Sometimes we have to work with x1, x2 with joint density, some given joint density, and we want to find out the density of x1 plus x2. Then can we use the Jacobian formula? Well, when we learned the Jacobian formula, it worked from Rn to Rn. But in our case, we have in place of n 2 because we are starting with two random variables and we are ending with just a single random variable. So you cannot use it directly, but indirectly we can use it. We turn it into a function from R2 to R2. I just add in the unnecessary thing y1 equal to x1. And y2 is the thing that is actually of interest. Now that it is a function from R2 to R2, we can use the Jacobian formula. We have this function, and of course it is bijective, because if someone gives me y1 and y2, I can recover x1 and x2 because x1 is just y1 itself and x2 is y2 minus y1. You subtract the first from the second. And the Jacobian matrix is very easy. I take the first component y1, partially differentiate with respect to y1 to get 1. I again take this, partially differentiate this with respect to y2, I get 0. Now I take this one, partially differentiate with respect to y1 minus 1 with respect to y2 plus 1. Its determinant turns out to be 1, which is anyway positive. So absolute value of the determinant is actually just 1. So density of y1, y2, call it gy1, y2, is pretty simple. All that I have to do is to write f x1, x2, but of course I have to write in terms of y1 and y2. So I will write y1, y2 minus y1. This is actually x1, this is x2. Multiply that with j, which happens to be just 1. So that is the joint density. Now our job was to find out the density of y2 alone. So now what I can do is that I can integrate out y1. I will just take this f y1 y2 minus y1. I want to keep only the y2 part, so I will integrate with respect to y1 minus infinity to infinity and give it a name, say g2 y2. That is the required answer. Now suppose I give you the extra assumption that x1 and x2 were independent, because that is the situation that we will be dealing with most often. In that case, this joint density will factorize. So you will have the joint density is, this is the marginal density of x1 and this is the marginal density of x2. In that case, if you just factorize it, you can write it as f1 and the first argument y1 times f2, the second argument y2 minus y1 dy1. Now this is an interesting way using which you can manufacture a new density from two given densities. So f1 is one density, f2 is one density, univariate densities, and if you do this process you will get the third density, and there is a name for this. It is called convolution. So we are taking the convolution of f1 and f2 and producing this g2. We have a symbol for that. We write g2 equals f1 and the symbol for convolution is a star, f1 star f2. It is just a binary operation. And you can convince yourself that this is same as f2 star f1. Probabilistically it is pretty obvious because this is the distribution of the density of x plus y or x1 plus x2. This is the density of x2 plus x1, but x1 plus x2 is same as x2 plus x1. So they should be the same. And you can just play with it, some substitution, etc. You can arrive at from one form to the other. In this exercise, I give you x and y independent. They have densities. X has density this, y has a very similar density, except that here I have lambda and here I have mu. Incidentally, lambda is positive and so is mu. Your job is to find the density of x plus y, and I have given you this formula so that you can readily use it.